just check. I hope I'm still with you, George, and with everybody.
Yes.
Yeah, I see more people join, so this is good. Okay, so today I will start with a proposition. Normally, I would start the session with a definition, but today I will start with a proposition. So the proposition is this: given an n-dimensional manifold X, and a k-dimensional manifold Y, the claim is that the product space, you know what the product space, when you take the product of two topological spaces, the product space is an n plus k dimensional manifold. So this is, in other words, this is a way of a handy way of generating new manifolds. This is actually one of the things that a lot of people, they do. You know, they want to work with higher dimensional manifold. They look at lower dimensions. They see two manifolds that they like, and they take their products. Obviously, it has to match the dimension that they want. So in this case, for example, look at this. So that means that if you take the product of the sphere and the circle, obviously you have 3 plus 1, 4-dimensional manifold. The same with the torus, and this can also be generalized to a d number of manifolds, obviously. So this is a nice way of getting new manifolds by taking the product of existing manifolds. That way, you're already familiar with the two or n manifolds that you are working with. It generates higher dimensional manifolds for you. Physicists do this a lot, especially people who work with things like string theory and these things. They are actually masters. There's someone was used to joke, they are masters of taking product manifolds. Okay. Another thing I want to, so this is a challenge, homework challenge. Before I move on, it's not that hard. It's not that easy. Well, it's not that hard really. It's a little bit more of time consuming, I would say, than difficult. So I would encourage you to try to see this, even if it's just for two two manifolds, and then if you can generalize it to more, that's even better. Okay, so another thing, this is more of a notational stuff, and this is something that you will see a lot. This is more of a notational awareness because you will see this a lot in physics, in books, differential geometry books that are tailored to physicists. So suppose we have this chart. You know what a chart is, right? Phi from an open subset of the manifold X to some open subset of Rn. So phi takes a point in U and maps it to a point in Rn. So this means that phi of P is just an n-tuple, right? Now, Rn obviously is a Cartesian product of R times R times R n times, right? So in theory, we can construct phi via several maps that we will call phi upper index I, that go from U to R. Okay, where the index I goes from obviously 1 to 3 to n. So you would have this phi 1, phi 2 to phi n for all p in U. So this is what physicists they think. This is what's called components maps. So very often the way, obviously we are working in abstract, in a concrete way of building this a chart is to build it by constructing the chart via these component maps that are real valued functions, because we know pretty well how to deal with functions that go to R, right? So that's one thing I wanted to call your attention. You will see this a lot. And another thing is that obviously we are using the notation phi, but in a lot of books, especially those who are that are tailored to physicists, they use the notation x. So, for example, for example, instead of phi of p, they would write x of p, and this would be like this in this case. yeah, similar to the thing. So this will be written like this. And another thing they do is the X upper index I of P often is abbreviated as XI, like this. Okay, so this would be, so for example, X of P then would become like this: X upper index 1 of P, X upper index 2 of P, and so on. Okay, and then this would be, then obviously they label it X upper index 1, X upper index 2, and so on. So this is just for you to be aware. We will not be doing this because we are mostly working in the abstract. But in a lot of books in differential geometry, especially the ones that are tailored to physicists, you have to overcome these notational annoyance nonsenses that they introduce. Okay. Okay. Is someone having an issue, or that's local to them, right? It's not me. I would say.
I think everything's still all right globally.
Okay. Good. Okay, so now we are in the thing, a very important concept. This is this thing of a chart transition maps. Okay, the name actually, chart transition map, is hinting into what exactly this in the thing in practice this is doing. We'll come back to that in a minute. This is essentially encoding something very intuitive that I hope the name gives you a hint of what that is. But for the time being, let's go. Let's look at this again. This is a proposition as opposed to definition. Yeah. So the claim is that given two charts, U1 phi 1, U2 phi 2, disjoint. Okay. Non-disjoint. Sorry, non-disjoint chart, meaning that their intersection is non-empty on a manifold. The claim is that this composition, phi 2 after phi 1 minus inverse of phi 1, which obviously goes from the image of phi 1 to the image of phi 2. The claim is that this map is a homeomorphism. I claim this is also trivial to prove because homeomorphisms 101. That both of them they are homeomorphism. The inverse of a homeomorphism is a homeomorphism. The composition of a homeomorphism is a homeomorphism. Okay, so this composition is called chart transition map from chart U1 phi 1 to the chart U2 phi 2. And I will abbreviate this in the notation by this phi 2 1. Okay, so phi 2 1 is just this composition. So this is the thing. Obviously, we are going from this chart to we are going from the first chart to the second chart. We can also decide to do the other way around, right? Go from chart U2 phi 2 to the chart U1 phi 1 via this composition here, which we will also abbreviate like this. Now, there is a very interesting relationship between these two maps, phi 2 1 and phi 1 2. I won't say it. If you know, don't say it, please, because in one of the exercises, this will play a thing. You will be able to, if you say it now, if you say it, you will already give away the challenge that I will give later. So, but there is a relationship between them, and I claim that you will be able, if you think a little bit hard, you will be able to see this. Okay. Now, I'll just ask, you can answer this, by the way. Can anyone see what this concept of chart transition is trying to, what is this trying to encode? What is this trying to formalize? A very intuitive notion. If you cannot, don't worry, because in the next slide where I have graphics and these things, you will probably be able to see. Can anyone, okay, so Barry said he rebooted, that's great to know. Does anyone have any idea what this is, what intuitive notion that this is trying to formalize?
Yes, but I don't want to be the spoiler.
Okay. So George knows, he doesn't want to be spoiler. So, okay. Anyone else don't want to be a spoiler? Okay, I claim that in the next slide, maybe it will help make things easier. Okay, so here's the thing. Apologies for my drawing. I was trying to use this thing to make these graphics, draw.io. It's a bit of a pain to put arrows. So the arrows are not that nicely the thing, but hopefully you can see. So this is the first example. So this is the chart transition from the chart U1 phi 1 to the chart U2 phi 2. So this is essentially, so this is their intersection here. This is U1, this is the map phi 1. This is their the image of the intersection. And this is the transition. So phi 2 of 1 is just this. So it goes from this intersection here to this intersection here. Okay. So in other words, imagine that you came this way. So you came this way, and then you said, you know what? I don't like this part of Rn. So this is essentially enabling you the opportunity to then go to another part of Rn that you might like to, you might love most, for some reason or other, because it's much easier to work with. Okay. So the same here also, the same notion here. In this case, you start here, and then you go this way. Okay, so you start here. You say, yeah, I don't like this part of Rn. I would like to switch to another part of Rn. So I think now a lot of people can see now what this might be encoding. Apart from George. Can anyone want to guess? Maybe George, you can spoil it then.
You are like joining regions together as you move around in Rn. You're also moving around your manifold. Mm-hmm. And from the example in the homework challenge of mapping the circle -1 point, that is a hint to that you can't always make just one map from your manifold to Rn and back. That even though everything is smooth, that there'll be a discontinuity. An example
of George use the word smooth. We will reserve that for time once we know what.
Okay, sorry.
That, yeah. But the physics guys, I know George is a mathematician, so he's looking at it from a mathematician. The physicist is there. I don't think there's any physicists on the audience here. So this is essentially what I'll go now. This is what physicists they call change of coordinates. So when you what formalizes that? So for example, you are in Cartesian coordinate, and then you say, okay, you know what? I would like to try, polar coordinate system, and then you switch. So behind scenes, all this stuff that you've been, everyone has been doing in calculus and whatnot, in anything, is actually being the formalization of this is this thing here. So this is actually tells us something very interesting also. These maps are obviously from one open region of Rn to another open region of Rn. So we can ask questions, that we would ask to any map from Rn to Rn. We could ask, for example, are they differentiable, for instance, So these are all questions that, this is the essence of the notion of manifold, is really, they enable us to outsource computation from an abstract manifold to Rn, because we know how to compute. We know how to do computation to Rn. So this is really the main point of these guys. They are the ones that enables us to really do calculus on an abstract manifold using Rn because of them. So this is very, very powerful. It might take, for some of you, this might take some a little bit of time for this all these things to sync. But as you go along, especially you think it through, it become more and more and more natural. With the physicists, they do this all the time on the thing, whether they're studying like classical, physics, or including general relativity, because it's a classical theory as they class it. Okay, so here's the challenge. Why I didn't want you to spoil the relationship between the two transition maps. I claim this is very easy if you think it through, but yeah. So again, I'm very lazy. I'm using the other examples. It's because these examples are very, I would say, are very easy to for you to do. The same with the sphere. They are like much more easier to work with, I would say, in order to convey the points. So here's the challenge is to find the transition. So I'm giving you charts. So the challenge is for you to, I hope this is a chart you have to verify. I give you two charts. Again, you have to verify if there are two charts indeed. And then the thing is for you to find the transition function, which essentially in our case, because you know already the individual chart, is to find their inverses. So in this case, for this one, you want to find phi1 inverse. For this one, you want to find phi2 inverse. I claim you will find something very interesting. Okay. And the second challenge is the first one is with sphere, and the other one is with this one is with the circle. So the same thing again. Okay.